One is the HETP method. In which case your column height, total column height or total packed height, that is equal to the HETP multiplied by your number of theoretical stages. You get HETP values that are tabulated for certain types of packing that's well known. For most other types of packing, however, you don't really get HETP values. So your HETP, for example, look at this factor dP, effective packing diameter. So this dP is equal to 6, 1 minus your void fraction over your specific surface area per volume of packing. This void fraction is tabulated for most types of packing, and the specific surface area is also tabulated for different types of packing. So if you calculate this packing diameter, then your HETP is equal to 1.5 times dP in the case of low viscosity liquids, and if you are using specifically Paul ring packings. In the case of structured packing, HETP is equal to 100 over your specific surface area plus a third. And that's applying to low viscosity structured packing. For viscous liquid, you can just assume it to be 5 to 6 feet. For pressures greater than 200 psi, you're just going to have a value that is larger than the following. If your pressure is greater than 200 psi, or you can take HETP to just be equal to the column diameter if your column diameter is less than 2 feet. Okay, so if you have these, you want to do this very crude approximation, you can find your HETP. Your MT you find using your McCabe-Thiele diagram, as you found your number of theoretical stages, and HETP times NT will give you your packed height. So that's one method. The disadvantage of this method is that it's very unscientific, it's purely empirical, it's often very inaccurate as well. The reason why you would want to do this is only for preliminary designs. If you want to try and get some quick ideas for costing, then you perform these calculations. But if you want a serious design of column height or packed height, then the other method use mass transfer theory. Where your packed height is equal to your height of a transfer unit multiplied by the number of transfer units. Where your height of your transfer unit is equal to your vapor flow rate over this mass transfer coefficient times your specific surface area times your cross-sectional area S. Okay, so that is the HOG here, and you multiply by the integral of dy over y minus y star. This is NOG, your number of transfer units. You're integrating from your outlet gas composition to your inlet gas composition for your solute. Now where does all of this actually come from? This comes from boundary layer theory. On a molecular level, in terms of boundary layer theory, how does a molecule move from the gas phase to a liquid phase, or vice versa? Essentially, it is assumed that, let's say if this is your actual boundary, so let's say if you have a liquid droplet here surrounded by gas, on a molecular level this exact point over here is represented by this line. That's your actual boundary or your interface. Looking at the gas around it, immediate vicinity of the, so you essentially have this here being your gas in the immediate vicinity of the interface, and the concentration of this gas in this immediate vicinity may be slightly different to everything else around, known as your bulk gas. Okay, and it's a similar case with your liquid. So that's your interface right here for this liquid droplet. The concentration here is different to what's right inside here, known as your bulk phase. So this is bulk liquid here. Now your gas, your bulk gas phase composition will be given by Y. So you have a certain composition. Once you get to the interface, however, because you have a driving force, a tendency for your gas to get into the liquid, so the vapor composition that's right at the interface will be lower than your bulk composition. Looking at the other side, your liquid composition for your bulk liquid is given by X. Your liquid composition right at the interface is slightly higher than your bulk liquid composition. And it's this difference here that provides the driving force between your gas molecules getting into the liquid. Okay, we're speaking specifically about the solute here. Solute moving from your carrier gas into the liquid, into the solvent, for example, or into the liquid phase in the case of distillation. Okay, now in order to describe this driving force that's given by an absorption rate in terms of the vapor phase is given by this formula. In terms of the liquid phase, we have this formula here. Okay, so that's one equation from boundary layer theory. In terms of what it means over here for us, if we're looking at a column, this is just trying to give you guys an understanding of where these equations come from. So if you look at any column, any packed column, you have your vapor moving up and your liquid moving down. Your objective is to get the total packed height, so that's LT. Now if I have to take a very small arbitrary section of packing of thickness dl, and looking at your vapor flows coming in and out and your liquid flows coming in and out, so I have coming out of here a vapor with a certain mole fraction of the solute, and over here I have vapor coming in and the solute mole fraction has changed, so that's V plus dy, and what's coming in here is your liquid with a certain mole fraction, and what's coming out is the same liquid but with a different mole fraction of your solute. Okay, now if we do a material balance of this, so just summing up your flows coming in and out, and also trying to combine these differences here with this rate equation, we ultimately get a material balance that looks more like this. And if we essentially rearrange this and integrate for this dl, we'll get our LT being equal to the following here. What is Y and what is Y star? Y is your actual vapor composition of your solute, and Y star is the equivalent equilibrium composition. So if this is your operating line for an absorber, for example, if this is Y, then your Y star will be your equivalent on your equilibrium line.
Sorry, sir, can you please repeat this again? Y star is the equivalent on the...
Yeah, so this is your McCabe-Thiele diagram. This is your absorption line. This is your equilibrium curve. So this Y in this equation here is your solute in the vapor phase. So any arbitrary Y over here, that's representing on your operating line. Y star is your equivalent Y on the equilibrium curve. So if I just go straight down, that would be my Y star.
Y represent the moles of the solute.
Yeah, the moles of the solute in the vapor, and Y star is the moles of solute that would prevail at equilibrium. Okay? Okay, now, if this was BSc level, we will dwell quite a lot on this equation and the fundamentals and all of that. Fortunately for you, you are more interested in application, right? In trying to use this to design the column. So ultimately, the long story short is we ultimately need to find this HOG and this NOG. Now, it's not really easy to get these two values. However, there are many approximations for them. Okay, now, for example, how are you going to really integrate this thing? Okay, now, if both your equilibrium and your straight line operating line are the same straight lines, then it's quite easy. However, if your equilibrium curve is very curvy, like this over here, and your operating line is straight, the distances are not always the same. Okay, so this integral is not always easy to solve. And for this HOG, this mass transfer coefficient is not always easy to get. So we're going to look at some technique on how to get these two values. Looking at NOG first. Okay, remember from our equations that we did in the previous lecture, if this is your operating line, the gradient of this line is L over B. If this is your equilibrium curve, we're going to call this gradient M. Now this curve might be a straight line curve or it might be slightly curved, but ultimately we're going to try and just get an average gradient M for this equilibrium curve. What we also need to look for are your mole fractions at the top and bottom of the column. So I'm going to specify your Y1. Which is your solute mole fraction. In the entering gas. Y2 is your solute mole fraction in the gas that's leaving the column, the leaving gas. Okay, then you can find your NOG using a correlation. That's your NOG, then you take your ratio of this Y1 over Y2. And then you have various lines. Okay, so that is 0. These lines here are representative of mv over L. Okay, so essentially you're going to find the gradient of the equilibrium curve and the inverse of the gradient of this operating line here. You multiply that, you get a certain value. It's dimensionless value. So looking at your Y1 over Y2, you just go up to wherever your mv over L is. And you go here and you get your number of gas transfer units, NOG. Okay, so that's one way to get this NOG value. There are other alternative ways depending on certain circumstances. There's various equations. Some are very complicated equations, some are very simple. But this is just one example. Now looking at your HOG, and as you can see, your NOG depends mostly on your equilibrium line. And essentially what you want to get out of your column and what you are putting into your column. So this depends more on the thermodynamics. Your HOG, as you will see, will depend a lot more on your packing characteristics. Now there's quite a number of ways, once again, to find HOG. Some correlations correlate HOG in its entirety. So you just get a correlation for this HOG. Other correlations correlate this mass transfer coefficient Ky, and then you multiply, you just include it in this equation. So you know what this is. This is your column cross-sectional area. You already found your diameter, so you know what that is. And this specific surface area depends on your packing choice. So you have correlations for this Kya value. Alternatively, you have correlations that just takes into account this entire thing. So looking at correlating your HOG in its entirety, you get the following equation. The HOG is equal to Hg plus mv over L times HL. This Hg to this GM. Sorry, we can just call it VM, not GM. Let's just use that. It's kg AW times your pressure. This VM is essentially your molar flow rate of your vapor per unit surface area. So per unit cross-sectional area. So that's V divided by S. Okay, so this would be in kilomole per second, for example, and this would be in meter squared. So this Vm is kilomole per second meter squared. Okay, your pressure, that's your operating pressure in bar. This AW, you have quite a long equation for that. So this is the effective interfacial area. The AW over A is equal to 1 minus. Okay, so you're essentially taking E to the power of the following. This is your critical surface tension divided by a surface tension of your liquid. Your liquid mass flow per unit surface area divided by your packing specific surface area. This is taking into account your liquid density. So you need to get your liquid surface tension. This critical surface tension is the surface tension of your liquid that's right on the packing. Okay, so for example, this depends on your packing materials. If you're looking at ceramics or steel packing, plastic or carbon, this value here would be 61.75. Okay, this is in millinewton per meter. And this liquid surface tension, that's something that's a property of the liquid that you can find. This A depends on your packing choice. LW star. So wherever I put a star over here, that means I'm talking about mass flow rate. So this is in kgs per meter squared second. The one without the star is in kilomole per meter squared second. Okay, it's just taking into account a whole host of properties to ultimately find this AW, which you will put inside here. Thereafter, to get your kg, that's depending on another equation. There's a lot of equations today. Okay, now DP is your packing size. You get different sizes of the same shape of packing. That's in millimeters. This is your specific surface area per unit volume of packing. Okay, that's your gas density. This dG here is gas diffusivity. Okay, that's another property. You have your viscosities. Your K5 is a factor. So it's 5.23 for packing size greater than 15 millimeters, or the value is 2 for less than 15 millimeter size packing. Okay, now you use this equation to get your kg. So that's the whole long process just to get ultimately this Hg value. To get HL, it's a similar case. So your HL, that's equal to Lm over KL. This AW is the same AW that you would use from here as well. And then you get CT, which is your solvent concentration. So let's look at that first. That's just equal to your density of your liquid over the molar mass of the solvent. So density of the solvent divided by molar mass. So that's easy. This Lm, molar flow rate of your liquid per column cross-sectional area, right? The same units here. Kilomole per second meter squared. So you have this, you can get this, you can get this. Looking at your KL, it's another equation similar to this one. Let me just take this out here. Liquid diffusivity, another AdP, the 0.4. Okay, so it's very similar to this equation for Kg. There's an equivalent KL. So once you get this KL, you can get your HL. So you're putting it in here. You have your Hg, so you can find your HOG. Ultimately, your total packed height is equal to this HOG times NOG. Okay, now this is just giving you all a basic idea. I will have these equations in the notes as well, with each term explained with the units as well. But just to give you an idea of what is being taken into account, all of the packing characteristics as well as your liquid characteristics, your surface tension, viscosities, densities, diffusivities. This is a lot more scientific than just that normal NT times HETP. Okay, so you want accuracy, you're going to get more complicated. Okay, so this is quite a long rabbit hole if you want to go and look into the various ways to find HL and HG, or the various ways to find this KYA, you're most welcome to do so. It's like a chapter on its own in many absorption and distillation textbooks. Okay, so this is just one example of the procedure. Okay, but that's ultimately to get your packed height. Now, other things that we can look at getting as part of your column design. Your flooding pressure drop. There's a very easy estimate for your pressure drop at flooding, which depends on your packing factor. Remember, your packing factors are listed in tables for various packing. You ultimately end up with a value of pressure drop that's in inches of liquid per feet of packing. So whatever your packed height is, to get your total pressure drop under flooding conditions, this is what you just multiply this value here, you can get your total pressure drop. Under normal conditions, there's various ways to calculate pressure drop. I'm just going to give you some easy ways. So you have an easy pressure drop correlation where you find your superficial gas velocity. The reason why we call it superficial gas velocity is because theoretically through a packed column, so this is your section of packing and your gas is moving up, theoretically your gas is not just going to go vertically upwards, it's going to have to go through all of the holes of the packing, etc., to ultimately get through. But superficial gas velocity is just looking at your vapor flow rate coming in here. So that's your vapor flow rate times maybe your density. And yeah, okay, as well as your molar flow rate. So that's your volumetric vapor flow rate divided by your cross-sectional area. And pi d squared over 4. You know what your column diameter is already. So you're getting your superficial vapor velocity, just assuming that the gas is moving straight through. So that's superficial vapor velocity, and also equivalently, your liquid coming down is also moving through quite a tortuous path, but we can assume our superficial liquid velocity, that the liquid is just falling straight down, so you get a liquid velocity as well. Now your superficial vapor velocity is on this x-axis, and you have numerous lines. And these are representing your various values for liquid velocity, superficial liquid velocity. Okay, so you can get it from 0 right up to around 80 meters per second. So just looking at your velocity ratios, you can correlate pressure drop. Again, this is in millimeters of liquid per feet of packing. And then to get total pressure drop, you have to multiply by your packed height. Another method to get pressure drop is to use your diameter correlation. Remember to get your column diameter. You had this Y value here, and you had your FLV. This top line here was your flooding line, which you use to get your flooding velocity. Now, if you already have your flooding velocity UF, your actual velocity will equal to F times UF, right, when this was 0.7. And remember, we had a number of pressure drop curves over here. If you have this actual velocity, you can calculate this Y value. Your FLV remains the same. So whatever your FLV is, whatever your Y value is, you see which curve it's intersecting here. And each of these curves has pressure drop values. It's not very accurate, but this is normally used as a start to estimate pressure drop. Then you get more complex equations. This is actually a bit more complex than this one. And you get various other correlations as well. Okay, and then another design aspect is, remember, for your column, you have essentially these liquid distributors. To calculate the number of these streams that you need, so the number of those distributors, you just had empirical correlation. So D over 6 squared, where D is your diameter in inches. Okay, now a lot of these studies, of course, have been done in the US, so you have a lot of these correlations working with these inch and feet and things like that, so American units. So you have to use your correlations in their correct units in order to get something accurate. Thereafter, the final value you can convert to meters or millimeters. Okay, so this will just give you a value. Some columns can have 120 to 150 of these distributors here to sprinkle the liquid over the packing. Okay, so we've looked at the packed height, we've looked at the diameter, mechanically we've looked at the number of distributors here. Thereafter, so that's essentially the main design issues, and we've also looked at pressure drop as well. Those are the main design issues. Thereafter, how many sections of packing do you need? That is ultimately recommended by your packing manufacturer, and supporting this packing, that becomes an issue of mechanical design. okay, which is under mechanical engineering. So that's all civil and mechanical issues. Okay, but as a chemical engineer, you are responsible for these specifications mostly. Those are the key things, and as you can see, it's not always very easy to get these. Okay, any questions? Okay, it looks like it's as we discussed in the previous lecture, it is very laborious, but ultimately the equations are not so complicated. It's all multiplication, divisions, powers. You put it into a spreadsheet even just once, you have it forever, and yeah, ultimately it's just following the procedure. Where there's no fancy integrations and things to handle. Okay, now what we've looked at is some of the simpler variations of these correlations. So just to make you aware, there are more complicated correlations that take more things into account, and within certain ranges of operation, different correlations have higher accuracy. It doesn't mean that if you have a more complicated correlation, it's going to be more accurate. It all depends on your conditions, your liquid and vapor flows, your liquid and vapor velocities within certain ranges, and also within certain types of packing, within certain liquid viscosities. Certain correlations are more accurate than others. Okay, and that's ultimately it from my side for column design. Next week we'll look at heat exchanger design. Okay, thank you very much.
Thank you, sir.